Matrices and systems of linear equations, part 1. Matrices. When we look at describing matrices as a set of numbers inside brackets here, what we do is we consider the size of a matrix or the dimension of a matrix. When we look at size or dimension of a matrix, we say that there are m rows and n columns, so our size or our dimensions are r by c, rows by columns, m by n. We use matrices to help us solve systems of equations. We can take a linear system and put it into matrix form, where we list the coefficients of an x, coefficients of a y. Our vertical line is the equal sign, and then those values on the other side of the equal sign. Let's look at linear equation number 1. Looking at coefficients of x and y, we have 2, -1, other side of the equal sign 5. 2, -1, other side of the equal sign 5. Coefficients of x 1, y 4, other side of the equal sign 7, 1, 4, 7. We've worked a lot in the last part with systems of equations, two unknowns. We can extend it to 3 equations, 3 unknowns. And the augmented matrix that we had before is just extended. Instead of an x and a y variable, we have an x, y, and a z variable. Our vertical line still means the other side of the equal sign, and notice that we're still just listing coefficients. 3, -2, 1 equaling 5. 3, -2, 1 equaling 5. 1, 3, -1 equaling 0. 1, 3, -1 equaling 0. Whenever we have a variable that's missing, we use a 0 in that position. That was really 0y. 0 times y is 0, and so that's not going to contribute to the equation. So then what are our coefficients? -1, 0, 4 equaling 11. -1, 0, 4 equaling 11. Where we looked in the last section, 2 equations, 2 unknowns, now we're just extending it to 3 equations, 3 unknowns. Our goal is still to solve a linear system. Okay, with 3 equations, 3 unknowns, we're going to look at solving a system known as Gaussian elimination. With Gaussian elimination, we're looking for 1s along the diagonal and 0s below. We work column on the left and go through each column to the right until we get that 1 on the diagonal, 1 on the diagonal, 0s below, 1 on the diagonal, 0s below, 1 on the diagonal. Here's how it's going to look by hand, just to kind of talk through a few things. In this case, we multiplied row 1 by, looks like a 4th, in order to get this 4 to become a 1. Then we're going to use this 1 to get zeros here. 1 times -3 and add to here would make that a 0. And so that's what's being done here. We're going to multiply row 1 by -3, add it to row 2, eliminating x. Okay, we can use this 1 to make this a 0 by multiplying 1 by 2 and adding. We're going to multiply row 1 by 2 and adding. That would give us a 0 here, and we can continue as long as we are looking towards our goal of 1s along the diagonal, 1s along the diagonal, 0s everywhere else. Now, in this form here, this is called row echelon form. Row echelon form. You have that 1 on the diagonal with 0s below. With row echelon form, now we have to back substitute to get our solution. So here we're looking at z equaling -2. X and Y are 0 in coefficient, so 0 times X or 0 times Y just wipes them out. Then we back substitute. Here we know 0x plus y plus 4z is equal to negative 7, but we know z is negative 2, so if I plug in a negative 2, I know y is negative 8 would be a positive 8 when I put over here with a negative 7. Y turns out to be 1 when we solve. Back substitution. Let's look at back substitution. Okay, so now I'm going to take this equation. I'll write it over here where we have more room. Y plus 2, oops, back up. X plus 2y minus z equals 1. But what do we know? Y is 1, so we're going to plug in y is 1. What do we know? Z is negative 2, so we'll plug in a negative 2, and we can backtrack to get y, backtrack to get x, and so that's why it's called back substitution. Okay, so 2 plus 2 is 4. 1 minus 4 would give us a negative 3. And like before, we were looking for an ordered pair, x, y. Here we're looking for an ordered triple, x, y, z. We found x to be negative 3, y to be 1, z to be negative 2, and that would be our solution. In the original equation, we should plug in these numbers into every equation to make sure our answer is correct. But if we did all of our work correctly, no matter which equation we plug in, x is negative 3, y is 1, z is negative 2, we're going to get a true answer. So this is called row echelon form. We're only interested in ones along the diagonal, zeros below the diagonal. On your calculator, that's your REF, row echelon form. Okay, so Gaussian elimination with back substitution. Now we have what's called the Gauss-Jordan elimination method, Gauss-Jordan. Not only do we want those ones on the diagonal and zeros below, we also want zeros above. That's the Jordan part. So Gaussian elimination, Gauss-Jordan, we're going to also work on those zeros above. And again, our goal is the 1 and then the zeros, the 1 and then the zeros, the 1 and then the zeros, the 1 and then the zeros. Once we get that 1 with zeros below and zeros above, we already know how to write these solutions because that's what we worked on in the last part. Okay, so what do we got? We have a variable x, a variable y, and a variable z. Okay, so we got a variable x, a variable y, and a variable z, vertical line, other side of the equal sign. When I look at this equation, we have x, and then these zeros wipe out y and z. We have x equals negative 3. We have y, because these zeros wipe out x and z, we have y equals 1. These zeros wipe out x and y, so we have z is equal to negative 2. And there's our order triple, negative 3, 1, 2 as a solution. This is preferred, and this is our REF. This is preferred because I don't have to use back substitution to get the rest of my answers. I just completely get to the answer with my zeros below and the zeros above. I get directly to my answer and I'm done. So this is the preferred method. This is what you want to use over RREF. Let me say that again. This is the method preferred, RREF. It's preferred over REF. Okay, a matrix is given. Determine whether it's row, echelon form. Determine if it's reduced row echelon form, and then write the system of equations for which the given matrix is augmented. Okay, so here's our diagonal of ones, correct? Nope, it's not a diagonal of ones. So this is not this is not row echelon form, REF. It's not reduced row echelon form. I don't have that one on the diagonal, so those are out. Now if we want to write the system for which the given matrix works with, we would just say x minus 7z is equal to 0, y plus 3z is equal to 0. We're just writing each equation. Here we would say 0 equals 1. Does 0 equal 1? Does not. So this would have a no solution. Okay, so determine whether the matrix is row echelon form. So row echelon form, you're just interested in the zeros below. So yes, row echelon form. If it's reduced row echelon form, then it has the zeros above and below the diagonal. And that's the case here. So not only is it row echelon form, it's also reduced row echelon form. That was that Gauss-Jordan elimination. Okay, there's our other side of the equal sign. Then we have x, we have y, we have z. Zeros wipe out the y and the z, so what we know is x equals 1. Zeros wipe out the x and the z, so we know y equals 2. Zeros wipe out the x and the y, so we know z is equal to 3. And so this one does have a solution, our order triple 1, 2, and 3.